value, I need to find out what the x value is associated with that y value. But in order to find the x value associated with a particular y value, I need to be able to find the inverse of this function. And this function just has no good inverse. This function, I mean, I dare you, Gabe tried yesterday, to solve for x in terms of y. It's like really, really hard, bordering on like impossible, like cubic form is required. Okay, so this is like a giant sad face. I'm getting much better at these. I do not know how to do this. Kellen, I understand how to do it like in principle, geometrically. I just can't actually do the problem. All right. Is there another way?
Yes.
Right. Can you tell me when it's rotated? So like vertical.
Is there another way? I know another way. Redrawing the same thing. Guys, let's just let our algebra dictate our what we do. Right? I have to revolve around the y-axis because that's what's going on. But like, what's the only thing I know how to do? You guys are like fading. I tried to draw the rectangle sideways and it just like didn't work. So let's just draw it vertical. Yeah, let's just draw it vertical. Not just because like I want to. All right. If I draw this, I probably should have stopped to talk about how could we talk about what kind of shape is formed? How would you describe this shape?
Sloping donut.
A what?
A flat bottom.
Say it again. Whoever was talking. Floppy donut? What the hell is a floppy donut? Yeah, it looks like a bundt cake. Do you guys know what a bundt cake is?
Yeah.
Sounds like butt, but it's not. It's bunt. Like Germans do, like D and T back to back like that. Bundt cake is like one of those cakes, you know, you get like a cake mold, nod vigorously if you know what I'm talking about. If you've never had bundt cake, Elias is volunteering to make us a bundt cake for Friday, so that's good. Yeah, Mark family, let's get some bundt cake on here on Friday. It looks maybe like a little bit of like a weird sort of circular mountain range with like a nice valley in the inside, whatever you want to call it. All right, that's what we need to find the value of. So I'm going to take the bold move of drawing the rectangles vertically. Here's the thing, Yoni, I'm doing that just because like I'm just like hoping for the best because I just know that for a given x value, I know I can find what this y value is. What is this y value? 2x squared minus x cubed. But what I don't know is like what the hell happens next. So what happens when that, basically the moral of the story is I do not possess the ability to decompose this bundt cake into washers whose volumes I can calculate. So Kellen, what I'm going to do is I'm just going to explore a completely new and different, unrelated, more creative way of partitioning the figure. We're going to partition the bundt cake now into like, I don't even know how to describe it. What you tell me. What happens when this representative rectangle is rotated about the y-axis? No, just the representative rectangle.
Yeah, it's a
tall washer.
Yeah, just a washer.
Yeah. Okay, tall washer, except the whole idea, the reason why the word washer is such a great word is because washers are very short. What does this mean? I don't know, what does that look like to you?
A pipe.
A pipe. Yeah, like a piece of PVC pipe or something like that. Or?
A tambourine.
One of the spacers.
Tambourine, but like not with it. Like a tambourine before you actually put the like stuff on. Like the wooden part of the tambourine only. Okay, good. Like a pipe. Looks like a ring maybe.
Looks like one of those tanks that they have dolphins in.
Yeah. Tanks with dolphins in. Yeah, good.
Aquatic tank.
Yeah, I think it looks kind of like some people say it looks like a toilet paper roll. That's like another thing, right? A little roll of toilet paper. I actually like that because, right, the cardboard is very, very thin. It also reminds me of like a city wall. There's like, if you had like a city and you built a giant wall around your city, the wall is very thin relative to the radius of your city. What's up?
This is where we don't do that here.
Okay, cool. Whoa. Geometrically, however, what is this shape? Say it again, check that. Hollow cylinder. Could you be even more specific?
It's a single roll of toilet paper.
Yeah, but can you describe it geometrically?
Like the piece.
Oh my god.
Bunch of circles just like stacked on top.
Bunch of circles. No, but that's not even.
It's like a circle but with a width. It's like a
It's-
circle with width. No, but like the circumference is width.
Cylinder minus a cylinder. Thank you.
Circumference with
This is just like a washer. Just like a washer is a cylinder minus a cylinder. This is also a cylinder minus a cylinder, right? But in a washer, the dimension that was really tiny was the height. In this case, the dimension that's really tiny is the differences in the radii of the cylinders. Follow? So for that reason, we give this a name. We call it a shell. Shell is just the math term for this shape, which is after all a cylinder minus a cylinder, but I don't want to use the word washer because the whole idea of washer is just they're really short. Shay, are you with me?
Yep.
What I'm proposing, believe it or not, is that we decompose this bundt cake into a bunch of little tiny toilet paper roll shell things and find the volume that way. In other words, that's a representative rectangle. I could draw another rectangle, and if I do that, what happens when that rectangle gets rotated around? A different little shell is formed. Are you guys seeing this coming together? This picture is pretty damn good, actually. Who needs animation? And now here's like my next little representative rectangle, which is going to be shorter, and then a little bit shorter, and then that's like another toilet paper roll. You guys see what's going on? So I am going to decompose this bundt cake, Will Hartman, into an infinite number of very, very thin, like shell things. In fact, to me, this kind of looks like, you guys know what Russian dolls are? There's like a little doll, and there's like a big one, there's like a big one, there's a big one, but the thickness of the dolls is quite small. We're going to basically construct the bundt cake by building off all these little shells. We're just going to do like that. Cool?
Cool.
Say cool.
Cool.
Say cool again, damn it. All right, so, good. Can we figure out the volume of one of these? I think we can. See, I think I'll do it over here. No, I'll do it over here. So here's a shell. Focus, please. Here's a shell. Let's say that the height of this shell is h, and let's let r be the inner radius and big R be the outer radius. When this shell is rotated about the y-axis, I get or when this rectangle is rotated about the y-axis, I get a shell. Right? What are the dimensions of this shell? So it's like pi r, so pi big R squared h minus pi little r squared h. Exactly. It's just the what's it called? Cylinder minus a cylinder. So let's factor out a pi and an h, and if I do that, I'm left with big R squared minus little r squared.
And that says like, and you can continue to do that as the difference between big R and little R, which is 0.
Yeah, hold on. Before you even get into the calculus, they want to just like talk about a particular one. So then this is big R minus little r times big R plus little r. Yeah. I can factor that as terms of squares just because I feel like it, not sure why. Okay, now comes something cool. Big R minus little r. Are you tempted to call that something? I am. I'm tempted to call that dr. Good job, person who said that. So this is pi h. I'll just call that like delta r. And now I'm going to pull a move. Here comes the move. I'm going to, so this is still r, big R plus little r. And I'm going to divide by 2 and multiply by 2 on the outside. What does that feel like? Okay. Griffin. Says me, Griffin. The volume of a particular shell, therefore, is 2 pi. This quantity, this big R plus little r over 2 thing, this is the average radius times h times delta r. Well, it's just the average of big R and little r.
Oh, I thought it was an average for like of all the different.
No, the average for a particular little r and big R.
Yeah.
So in fact, it's just this little point right here. It is that's what big R plus little r over 2 is. Okay. So, guys, I think that I now understand this well enough that I can start to add these on. Because after all, Griffin, Riemann sums say I can pick an arbitrary point, I can pick whatever point I want in any particular subinterval, right? So I'm going to choose the midpoint, and then it's going to fit this formula exactly. In other words, here comes now the real problem. I'm going to go from A to B. I have some kind of function. Here's my function. And what I want, the overall goal, is to find the to find the volume when the region under some function is rotated about the y-axis. And where it's inconvenient for me to do it sideways. So what do? Formally, I take the interval between A and B and partition it up into subintervals. And so that's like x1, that's x2, etc., etc. And then I go to the ith subinterval, and on the ith subinterval, math says I'm allowed to pick whichever point I want, right? So I choose the midpoint. So that's x sub I, I'll call it x sub I star, but just between me and you, it's the midpoint of the ith subinterval. And then I'm going to draw the rectangle whose height is determined by the value of the function at the midpoint. And now, what?
Could you just like do?
Wait, hold on. Can you just let me finish? Okay, good. All right. So then I'm going to take this and I am going to rotate it about the y-axis, and a shell is formed. And what is the volume of that particular shell? What? No. The volume of that particular shell, as we just calculated, is 2 pi. The radius of the shell, or the average between the inner radius and the outer radius of the represented rectangle. So that's just x sub I star times the height of the shell, which is f of x sub I star times delta x. Are you guys with me? This just follows straight from our geometric analysis of the shell over there. It's 2 pi, the radius, times the height of the shell, times the thickness of the shell. And what am I going to do with all these guys? I will add them up. Because that is the volume of one shell, and so if I take the sum from I equals 1 to n, and then I take the limit as n goes to infinity. Does this all making sense? Sprinkle some magic calculus pixie dust, what happens? Integral from A to B. Yep. 2 pi integral from A to B, x f of x dx. Cool. Okay. So Callum, that's kind of like everything you need to know. Instead of memorizing this formula, however, has anyone seen something like this before? Does this 2 pi RH thing kind of sound familiar? It's like the lateral area of a cylinder, right? Yeah, in fact, the cool thing to do is to take this guy and unfold him. Right? If you give me this, take this shell, cut it, and unfold the city wall and spread it out, what shape is formed? Yeah, a rectangle. In fact, technically, it is like a rectangular prism because it has some tiny thickness. And what's the height of this thing? This is h. What's this amount? Yeah, this is just like 2 pi r, right? The circumference when you unfold it. And then the thickness is like, delta r, basically. So the fact that that each individual shell has volume 2 pi RH delta R should feel like intuitively correct. Okay? And then once you can find the volume of one shell by the idea of integration, we just add them all up and take one. How do you feel about this? Okay, that's the theory. Now the practice. Nikili, can you give everybody one of these? And we're going to do as many problems as we can before the bell rings. Ooh, which is going to be 2 problems. We're going to do number 1, and we're going to do number 3 or something like that. Do number 1 right now. The second you get the worksheet, Nikili, faster. The first problem is actually just this problem. Go. Okay, wait, hold on. I'm sorry, man. I want to finish this lesson. Okay, good.
I think that's it.
Go.
Any questions?
Fine, man. Yes.
No, it's still.
Oh, here we go.
Can we just skip number 1?
No, I want to do number 1 because we haven't done it yet. We just we talked it out, but we haven't actually done it.
No, number 1 is.
Nope. Oh. Oh. Is that a typo? It is.
She was the one.
Sorry. Change that to y-axis.
Man, how no one catch that mistake in like 10 years?
Yeah, number 1. Number 1 was supposed to be the problem that motivated this whole conversation. In other words, we should be revolving around the y-axis.
Are rotating on the y-axis.
Oh, it does say that.
It
You just
says X
did
for
it.
my-
It's an English thing, Yoni. English. It's a long sentence with various subordinate clauses and things like that.
Ooh, subordinate.
Rotating about the y-axis, the region bounded by the x-axis. Yoni just demonstrated, I planted this comment in the audience prior to class to demonstrate an important fact, which is you need to read the freaking question multiple times extremely carefully. Make sure the question...
I read it.
Okay, good.
I did read it. I corrected Yoni.
Hey, did. Oh,
I did. I said you're
good. Oh man, I love period 3. Woo.
There's X in this one. Look at you.
Detrimental.
I didn't that.
That wasn't this annoying when I was this age. A lot of people, a lot of posts.
Is it too much?
Okay, so you make a graph, you label your curve, you shade your region, you indicate the axis that we are rotating about, you try to do washers, you cry, then you say, hey, I'm going to do shells, and draw a representative rectangle, and then I think it is useful to draw actually draw the shell, and if you want to, you can draw the whole bunch cake. What is relevant for me to be able to calculate the volume of that shell? What's relevant? I need to know the height. So for a particular arbitrarily chosen x value, I need to know both the radius of that shell and the height of that shell. The radius of the shell is x, the height of the shell is 2x squared minus x cubed. Got ya? Okay, what's the volume of a single shell? The volume of a single shell is 2 pi r, which is x, times h, which is 2x squared minus x cubed, times dx. And then we integrate from 0 to 2. How are we feeling about this? Good, do the integral and then flip to number 3 on the back. Did you guys get 16 pi over 5? Okay, if so, you're probably awesome.
That's really good.
Alright, now, number 3, I'm just gonna warn you right now, you need to be really careful about this. This is kind of tricky, and it's very important that you draw yourself a really nice picture of the situation. The bell's gonna ring in about 3 minutes, but we're finishing this problem.
The camera has like 5 minutes left.
Okay, good. We only have 3 minutes left, so we'll be good this time, I think. I didn't heed your warning last time, though, man. Okay, no, number three, fast. Number 3. Come to that, number 3.
Imagine of the hump. It's like a donut. It's like a half of a bagel. That's what I meant. No, it's not. It's just bumpy. No, it's, yeah, so it's half of a bagel.
E squared.
Not quite, though.
It's squared.
Parabolic.
Bagels are circles.
Alright, so y equals x minus x squared and y equals 0. So let's try to get a picture going of this thing. So this is going to be, can you guys stop arguing about bagels? Making me hungry. So I take the curve x minus x squared, that's just an upside down parabola with roots of 0 and 1, agree? Alright, thus the relevant region is this one. Alright, but what am I rotating it about?
The x equals 2.
The line x equals 2. Yeah, so this is like a whole new world we're in now. Good. Suppose I choose to do this with shells. Please draw your representative rectangle, key step. Alright, and now, in order to accurately figure out the volume of that shell, I need to know the dimensions of that shell. So I pick an arbitrary x value. Everything is in terms of an arbitrary x value. I think it's a key psychological move, to draw the x in. And now say, okay, what does this shell look like? Says me, the shell looks kind of like this, right? So there are 2 or 3 things I need to know about that shell in order to be able to find its volume. I need to know basically the radius and the height. What is the radius of that shell?
2 minus f of x.
2 minus x.
Or 2 minus x.
Good. Yeah, the radius of this shell is not x, right? Some people just memorize that formula, 2 pi x f of x. That's not correct. It's 2 pi r h, delta r. In this particular case, the radius of the shell is by definition, like the distance that the shell is from the axis of rotation. But having chosen my arbitrary x value, I think curly braces are key here, the radius of the shell is 2 minus x. And the height of the shell is x minus x squared. Okay, good, perfect timing. Thus, what is the volume of this solid? Please make sure the camera's on me. It is integral from 0 to 1,
2 minus x.
2 pi r, which is
2 minus x.
2 minus x,
X, and then x minus
h,
x squared.
which is x minus x squared,
dx.
dx. And then you integrate from 0 to 1.
You just do
We got this?
Yes.
Okay, cool. Okay, good. That's basically the last new thing we're going to learn this year, that we might do something else. On Thursday, probably have like a big quiz on this. Friday, probably have like a quiz on this topic on Thursday. So there'll be homework on cross sections, some from this worksheet. There'll be homework on shells from the book. You can finish this shells worksheet up with the entry up on deadline. Any questions about what's going on?
Are we ever going to get this all tested?
Yeah.
They're really hard.
Turn that off.